Okay, so now we're going to see how we can use code from other source code files in our own programs. So we're going to look a bit at how the namespaces work in Python. We already saw that functions have their own namespace, their own universe for the variables. But we'll see where each name exists in the code and how we can import code from other files. And then we're going to use that for plotting. So we're going to import code from a plotting library, and we'll use that to make graphics. I'll start with a simple plot example, talk a bit about unit tests, which are the tests we do to the parts, the pieces of our program, all the different functions. And then we're going to see a more realistic example, a bit more complicated, but to create an animated plot. So let's start with how names are organized in Python. Each namespace, you can think of it as a sort of a dictionary where you have this association between the names of the variables and what objects they refer to in memory. And there are different namespaces in order to allow different parts of your code to work separately using potentially the same names but without interference. For example, the split method that we use for strings belongs to the namespace of each string object. If you try to do split without anything else, then you'll get an error because the interpreter doesn't know what that split name refers to. But the split that belongs to the namespace of this string, it knows because there is a method that belongs to the string that has that name. So this is an example of a name in the namespace of the object. In general, there are these 4 levels, or we're going to talk about 3, the enclosed one, we're not going to see examples of that now. But basically, there are these levels of namespaces, of dictionaries, so to speak, where the interpreter is going to look for the names. So it starts at the local level, for example, in the same method or the same function, and that's where it will begin assuming that the name is there. So if you have, for example, in this function, when you say print var2, there is a var2 variable inside the function, so this is the one the interpreter will use. If it does not find the name in the local space, it will go to the enclosed. This would be if you have a function inside another function, so we'll skip that because we're not going to use that now. But then it's going to go to the global namespace. The global namespace is the namespace for the file, the module that you have. So one file in Python is one module, and everything that you declare there is in the global namespace of that module. So if there is a variable var1 there, if inside the function you write print var1, there is nothing called var1 here, so it will look for the name in the next level, which is the global namespace. And finally, it will look at the built-in namespace, which is the namespace for all these reserved Python names and functions like print, def, things like that, which are the last ones. So these ones are accessible from everywhere. So if you call this function, the first var1 will print this string here, and then the second one will print that. If you try to outside call var1, this exists in the global namespace because we ran the whole script, so we have access to var1, but we don't have access to var2. This only belongs to the function, so from outside the function we cannot get that, because the ordering is always from local to wider range. This is part of the syntax. Even if you don't have arguments, you always need parentheses because they're part of the syntax of defining a function and also for executing the function. So even if you don't give anything to the function, if you don't put the parentheses here, you're just referring to the function, not executing it. And there you need the parentheses because they are part of the syntax for defining the function. To declare the function, In theory, you could write the function in the console if you wanted. So if you write def something, but usually you're going to write the functions in the source code, and then either you run everything with F5, or you select the part that you want, and you can use F9 or the other icon that has a black arrow that copies this thing to the console. But it doesn't matter where you run this, if it's directly in the console or as part of the whole script. What matters is that you run this so that the interpreter creates the function. So here we don't have access to the variable there. If we change the value of this var1 and now run the function, it will print this different value because we are changing the variable in the global scope, and the function can access that. But even if we create a new variable var2, it still prints the same because this one belongs to the function and it doesn't change. So the order is always from local to global. That way functions can access global variables, which can include other functions. That's why we can use different one function calling another inside our program. But from the outside we cannot look into the variables of the function, and that preserves the isolation of the code. So let's see another thing, which is importing names that are in different modules. We've been using modules just by writing everything in the same file and executing, but in Python we can organize our code into different files and then import things from one file to the other. And the import statement, what it does is to fetch whatever we are importing into our own namespace. For example, suppose that we stored that script for solving quadratic equations that had this solve quadratic function. We saved that as quadratic.py. Then if we are working in the same folder, we can import that module, so that file of Python code. And now everything that belongs to that module will be inside that namespace. So this quadratic corresponds to the file that is there, will be an object that has, for example, the function that's inside the source code, the solve quadratic function. So we can import that and then use the function to solve an equation. Well, if you're using your own codes, it has to be in the same folder. You can create packages and install them in the Python folders, but then you need to tell the interpreter where these are. These are configuration files, so if you install some library, you don't have to worry about where it is because it's registered with the interpreter. If it's one of your own files, then you need to put it in the same folder, or you need to create a folder tree with some specific files that indicate where the rest is. But this is usually in practice what you'll do is either you're going to install a library and then you don't worry because Python knows where to find it, or you're going to use your own code, and in that case it's more practical to have everything in the same folder. Another possibility is that you add new paths to the system path for Python so that it can find your other files. But that's, I can talk a bit about that at the end of the course, but that's really not necessary. Usually, if you want to organize your code, you can just put everything in the same folder in different files, and that's good enough. So this would be one file called quadratic.py that is in our folder. We import that code. So when Python reads this import statement, it will run everything in that script, in that file, and we'll have in memory all these functions that are declared there, so we can access them inside the space, the namespace of the module. Yeah, it must be, that's the requirement. So if you want to import code from a Python file, you must use the name exactly of the file without the extension, and the extension must be .py. Yes, it is case sensitive. There is a bit of a problem in Windows because Python is case sensitive and Windows file system is not. So if you keep everything with the same case, it's okay. If you don't, then you can have problems with Python, and then you cannot change the name in Windows because it thinks it's the same name, and it will be a bit messy. But so avoid that. If it's in Linux or Mac, you don't have a problem because the files are really different and in the file system too. But yes, it should be the same case. So this, in this case, we import the whole module as an object, and we can access the function that belongs to the module. We cannot access the function just like this because this does not exist outside the namespace of the module. It's something similar to what happens with the split example here. So split belongs to that string object, and the quadratic, solve quadratic belongs to the module object. Okay. But we can import in another way. We can do this from some module, import whatever we want. So typically, if we need lots of things from that block of code, that module, we can just import the module and use different things. If we need one specific function or object or variable from there, then it's easier to do from that module, import this specific name. And now we import this name from the module into our own namespace, and it will work as if it belongs to our own module. Note that this function, solve quadratic, may have to use other functions in the module, but that works okay because every time we do some import, Python will run everything in the modules we are importing. And in all modules that those modules are imported and so on. So the interpreter will have everything in memory that it needs. But we're just pulling the name into our own namespace so that we can use that function from our code. Another possibility is to give an alias to what we're importing. This is sometimes useful because you may want to import some code, for example a function or a module that happens to have the same name as something else you already have. So and that would be tricky. You'd have to change some names and so on. So Python allows us to do this, to give a nickname to whatever we're importing. And in this case, we're importing the quadratic module, but the name we give it in our own namespace is this QD. So now we can do the same like we did here, but instead of using quadratic, we use QD and we refer to that module. So basically, you can import modules, you can change the name that you import while keeping the reference to what you're importing, or you can import specific elements from other modules. So this way, you can easily reuse code that was written for some other purpose, or that is stored in other modules, or even organize your code. If you have a large program, it's useful to organize things according to different types of tasks they are performing in order to get things a bit more easy to understand and not everything in the same file. So let's see how we can do this for plotting. We're going to use this library, matplotlib. This library has lots of modules, so it's actually a tree of modules, and sometimes it happens that you want to import one module from one library, and you can also do this by indicating what the namespace this pyplot belongs to. So pyplot is one of the plotting modules we can use from matplotlib, and since this is quite a bit string, matplotlib.pyplot, the convention is to import this as PLT. So now it's easy to use functions from that module just by typing PLT dot whatever function we need. To install matplotlib? Well, if you don't have it installed, you can use pip, for example, and install the library. Pip is the Python installer manager. But if you installed Anaconda, like I recommended, you already have this. So Anaconda is an installation of Python with many libraries and includes all the libraries we're going to use in this course, plus other libraries that we're not going to use. So if you installed Anaconda, you should have. If you don't, I can give you a hand. But Python has an installation as a specific program to deal with installing these different libraries. It's called pip, P-I-P, and you can use that to install other packages. No, no, because if you install it, then it's installed in the Python folders, and the configuration files are updated, so the interpreter knows where this library is. You just need to import it, and since it knows where it is, it will work. Okay? In R, okay, but no, this works different. As long as the interpreter knows where the library is, it's okay. So here is an example how we can do a plot. We import the pyplot module, which has the functions like plot, for example. And this plot function, all you need to do is to put the x values and the y values, and it does the graph. Now, if you're using the IPython console that you have there, you don't need to use show, because the console, if there is a graphic object in memory, it will show that graphic object and then delete it. And the console does that automatically. If you're not using the console and using your own program to run separately, then show is what you use to create a window where the graph appears. So you'll see, in that case, you'll see the graph appear in a new window. While you're working in Spider, all you need to do is plot, and then the graph will appear on the console. Okay? Yes, but you need to run.
Yes, I
I don't know, maybe there is a comma missing there. Okay? But we can see that after. Okay, just let me. Okay, we can see that after. So this, if you're using the console, it will display on the console automatically. If you're writing some program that you need to show the graphs in Windows and using it outside Spider, then you need show to create the window. So this is just a very basic plot. Let's see an example of how we can do this in practice. So we have this file, a CSV file like this, which has the estimated tuberculosis loads in different countries in different years. So, for example, we have here Afghanistan. This is the ISO 2 codes and ISO 3 codes for the country, the region code, and so on from the World Health Organization. Then we have the year, and we have the estimated population for the year, and then the incidence values in infected people per 100,000 inhabitants. So we have the estimated, the lower bound for the estimate, and the upper bound for the estimate. So this is a CSV file, comma-separated values file, which has text values which are quoted with quotation marks, and numerical values too. This is the text file. We could read this with read lines and then parse everything, but now that we know that we can use code from other libraries, we'll use this CSV library that has functions for reading this type of files. So usually, if you're using data files that have some standard format, there is some library to read them, and you don't need to code the parsing every time you're using them. So you're going to import CSV. We're going to open the file. So CSV Reader receives this object for reading the file. And then we have to give the reader function of the CSV module some parameters to tell it what's the format of the file. So the double quote is the quotation character for text in our file. The delimiter is a comma, it's what's separating the values. And then we also ask to quote values that are not numerical. So basically, things that are like this, it will retain as strings. If they are like this, it will convert to numbers when we get the result. Because we don't want these values as strings, we want the actual numbers. I think so, because it has the quotation characters there. So if it's explicitly marked as text, it will not be converted. I'm not absolutely certain. You can check. Yes, I think that's we can test that, but I think that's the behavior. In any case, these kinds of functions, you're not supposed to know memorize this. So every time you're using a library, just check the documentation, what's the parameters, and test things to see if it works. But the main idea is that you don't have to code for parsing all of these different formats, because usually you already have some library that does that. So Google how to open some specific file in Python, and you'll probably see which library to use, and then you just use that. So now this will return an iterator, an iterable that can look through all the lines in the file, all the rows in our CSV table. And if we use this list function receives something that can be looped through, so something that is iterable, and returns a list with all the values that it outputs. So if we use list on the CSV file, we get a list with all the rows in this table, but they will be like this. So you see, so it's really text. We have here the evidence. So the 004 is as a string, and we have this file parsed into a list of lists, in which each list corresponds to a line, and the numeric values already have been converted into numbers. So this list will be the first line of the text, this list will be the second line, and so on. So we have a list of all the rows, and each row is a list of all the cells, and all the various values are converted. And this just by using the CSV library. We don't have to do this by hand. And now we can look at the values on the table and extract those that we want. So, for example, we want to get the infection rate from this table for a specific country. Note that we have all the countries here. We have Afghanistan, Andorra, and so on. We have all the countries, and for each country there are many entries because we have different years for each country. So if we want to extract the year and tuberculosis load for one country, we need this function, but basically we give it the table with the complete set of data and the three-letter code for the country. So this is what we have on this column here. This is a three-letter code for the country. And now what this function does is we start with an empty list. We look through all the rows in the table, and if the third column, so in the row, when we do this for row in table, row is pointing to the first list first, and then in the second iteration to the second list, and so on. So that row variable is referring to each of the lists that correspond to each of the rows in the file. So now we're going to see if the third element is equal to the code. So the third element is this three-letter code on each row. If this one is equal to the code that we gave there, we're going to take the 6 through 10 columns, which are these values here, 6, and then 8, 9, and 10 in the order, which is the year. We skip the population, we don't want the population, and then we have the values for the tuberculosis load. The expected, the estimate, the lower bound, and the upper bound for the estimate. So basically, what this function does is this: we want the infection load for Portugal from the table, and we get a list of tuples where we have year, the estimate, lower bound, and upper bound only for Portugal. So these are the values extracted for these countries. And we can do this for any country and extract the values. Now we want to plot this, and we have these values for each year as tuples. There are simpler ways of doing this. We'll see next week how we can use NumPy with this kind of metrics. But now we're just using the matplotlib to plot, and we need one list with the years and another list with the value we want to plot. So we need to break this down into separate lists. One with the years, one with the estimates, the lower bound, the upper bound. So we can do this with a simple function. that receives as data a list of tuples, and this is the column that we want. And so generates an empty list and then goes through all the rows in this data matrix, that is something like this, and gives us and appends to this list only that specific value. So if we want the first element, which is the year, we convert the data to a list and we get a list of the years. The second column is the estimated tuberculosis load. We get the list for that value. And this we can use to plot. So here you see that we are using lists of tuples, again, like we did with coordinates. They work mostly the same way, except that when you create a tuple, you cannot change what's inside the tuple or change the size, remove or add objects. So tuples are immutable. And this is basically another example where it's a good idea that these are tuples because the meaning depends on the position. But this list will have to grow, so we cannot create that as a tuple because we want to add elements as we are creating the list. Another thing, when we want to do the plot, we get the whole table and the code for one country. Now we get the data for that specific country, and we're going to extract into different variables the year, which is the first column of that table, that data list, the estimated tuberculosis load, which is on the second column, and the low and high boundary for the estimates in these columns. We can actually do this in a lot simpler way using this zip function. This zip function in Python takes a series of arguments which can be iterated, so are sets, and then returns the first one and the second. So it basically builds tuples with the first item of each of the intervals, then the second one, then the third one, and so forth. So basically it does that kind of thing in one go. However, I'm not going to detail this because this is just to let you know that there are lots of things that I'm showing here where we are doing step by step unnecessarily. So if you learn more Python, you can simplify the code because there are shortcuts for those things. But it's not really important to start learning the shortcuts because the important thing is that you understand the steps, and then as you proceed you can start learning the shortcuts. The other way around will not work if we start with the shortcuts. So let's ignore this, but just keep in mind that you will have more code usually in this course than would be strictly necessary to make things work, but the idea is to understand how things work in detail, and then if you start getting more comfortable, you start learning these little tricks that speed things up. Okay, so now this would be the plot function. We receive into this function the table with all the countries, so this initial one that we read here from the file, and the code for the country we want to plot. This function will call that getCountryInfection function to receive this list with tuples of 4 with year and the estimates for this country only, and then decompose that into 4 lists, one with the years, one with the estimate, the lower and upper bound. Now we create a figure. This is a bit more complex, this plot, but you can start with this figure because one of the things you can specify is the size of the plot. This fixed size argument, we set it to a tuple 10, 7. And here we are seeing a new way of giving arguments to functions. So far we have seen only that we are providing values in the same order in which they are in the parameters. So the arguments are given by the same order as they are in the parameters. But there is one alternative way of doing this, which is to tell Python to which parameter we want the value to go by giving the name of the parameter. And this is especially useful if you have functions with many parameters. All of them have some default value, but you can specify that you just want to change that one. And this is what we're doing here. There is a parameter for the figure function called fig size, and we are telling the Python that only that parameter will change. The rest will leave as they are. And this is a tuple where you give the width and height of the image where the graphic will be drawn. This is in inches, but in practice it's arbitrary because it's in the monitor. Only when you save to file, the inches are multiplied by the resolution in dots per inch to determine how many pixels the image has. But in any case, you can use this to control the aspect ratio of your figure, if you want the figure to be wider or taller, depending on what you want to do with the graph. And now we're going to do several plots. And if you do call the figure function, you create a new figure. If you just do plot, you are plotting always on the same graph. So we're going to plot the estimate, the high and low bounds, all in the same graph. And this is a format string that, if you're familiar with MATLAB, you have the same kind of thing. So basically, this is a short notation for specifying the color, the kind of line that is joining the points, and the symbol in the points. So in this case, K is black, and a dash means a continuous line, a minus sign. And we are using a black line, a red line, and a green line to plot the three values. Now we can set the title. So in this case, we put infection load 4 and add the code for the country. And then we show the plot, and this is what we get in this case. So this would be testing our functions. We load the data from the file. Then we get the country infection from that table. This would be the test for this function here. We don't need that for plotting. And then we can test the plot function by giving it the whole table and the code of the country that we want. And this is what the plot function will do. Note that the plot function has no return, because this one does not return any value. It just shows the graph. So we just leave it like this, and when the interpreter reaches the end of the function, it just returns none, and the function is over. So now we can create this in our script, and now we can do some tests and document our script. So testing each step of our program is important, because if you spot some error after you started fitting everything together, it's harder to tell where the error is occurring. Whereas if you test one function thoroughly before going to the next, every time you find an error, you know that it's the function you're working on at present. It's also important because sometimes you need to change the code. You need to add new functions or update something, or some format changes, and you should run all the tests again because things may have broken due to some error. So it's good to incorporate tests into your module. The thing is that we don't want the tests to be run every time we are using the module, because we may have many tests and the output of the tests and so on. We only need to run them when we are testing the module. But there is one useful thing in Python, that is all modules have this name attribute. This is a special attribute, so it starts with 2 underscores, name 2 underscores. And this is set to this string, 2 underscores main 2 underscores, if this is the module that is being executed, if it's the main module in the program. If it's imported from the file, then the name is the name of the file that's being imported, so the name of the module. So this way you can check whether the module is being executed as the main module or simply being imported by another part of the program. And we can put our tests inside this check, so that if we want to test our module, we run it on Spider, for example, and it runs all the tests. But then when we are using our module by importing things from the module, the tests are not run. So this is one example. We can add this to the end of our script. If the name, this is an attribute that Python creates for each module. If the name of this module is main, it means that we are running this module and not importing it from somewhere else. In this case, we're going to load this file, which must exist in our folder. We're going to print the results of the table. We're going to get the country infection and print that data, and then do the plot. So this is basically this test that I showed. They're all automatically run there every time we run the module. But if we import the module from somewhere else, when Python runs all the module to create these functions, this will not be true, so all this will be ignored and the tests will not be run. This is a practical way for you to have the tests, the unit tests, all in your code, easily accessible, so you just have to run and you run all the tests, but still not bother you when you use your code as part of your program, because then you're just importing the module. Yeah.
If you have the file inside a folder, or should you write the...
Okay. So you can write a complete path to the file. If it's in the same folder as you're working, you don't need that. If it's in a subfolder, you can just type the subfolder there. Or if it's in a fixed folder, you can put c.my document. Yes, all the paths until the end. There is one slight trick that in Python, the backslash is reserved for special characters, like the new line and tab and so on. And Windows uses backslash for the file folders, so you either put 2 backslashes instead of 1, and in that case you're telling the interpreter that's really a backslash and not a special character, or you can use the forward slash, because the division like in Linux or Mac, because Python interprets that as being a folder too in this case. So that would be the easier way. Just ignore the way Windows does it, and do it like a real operating system would do. Okay. So this way we can put the testing code there. And now, if we want to use these functions, we just import them, and the code and the tests will not run in that case. Another thing that we should do is to document our module. So this is the module that does the plotting of the tuberculosis files. We can start with this string, so you'll have that UTF-8, so on, in the beginning, but then you can put this string. We use the same 3 delimiters in the beginning and the end to have a string that is a block of text. And now we can put some documentation on how to use this module. The reason for this is that you can also use help on the module. Help works on any object that has this kind of documentation. So if we import the tuberculosis plot module that we wrote and then use help there, we see what the name of the module is, but then we use this, we have this description here. So we have this header, and then the description that we have here, it appears when we do help. So if you document your modules with this format, it's easy. If you don't remember how to use them, just type help, or if someone else is going to use them, you can add examples of how to use them and so on, and that makes things simpler. And now you can import the function. So for example, from tvplot, we import load data and plot country. We do not need to import the intermediate function there to get country infection, because that one is used by the plot function, but we don't need it directly. So we just import this one to load and to plot the country, and now we can use the functions there. And if we do this, if we import it in this way, the tests are not run. The tests are only run if the module is run on Spider, for example, or if you run it on the console. So let's see an example that is a bit more complicated. There is this is a very good site for data on countries, the Gapminder. You have some good visualization there. And we'll do something similar to what we have in the site, just for this demonstration. So you have Excel files with indicators of development for the country, things like life expectancy, population, gross domestic product, and so on. We're going to use these 3, life expectancy, population, and per capita GDP. Each of these files has one top row with the years, and then one row per country where we have the data for the year, or an empty cell if we have no data. And these are Excel spreadsheets that you can download from the site. So what we need to do first is to get this data into our program. And the problem here is that, unlike what we had in the other case, this has many holes. So we can have data for some years and then missing data and so on. So we cannot put everything in a table because each country can have different numbers of values. And also we are dealing with different series. So we have the life expectancy, the population, and GDP. They're all different data sets. And what we want to do is something like this. We have China, Portugal, Spain, and Germany. So that's Portugal in green, Spain in yellow, Germany in black, and China in red. And we want to plot over the years what is the population. That's the size of the circle. And then we have GDP per capita in the x-axis on a log scale, and life expectancy on the y-axis. And this tells us how the countries were developing during these years. So this is what we want to do from that data. And now we're going to do this step by step. This is a bit complicated. Again, you'll have lots of details. But the idea here is that I don't want to mislead you. So I could simplify the problem. Then you would see, oh, that's easy. But then you would try to do something for real, and it would not be easy. So when you're dealing with real data, it's usually not trivial to solve the problem. But at least this way, you know the degree of complexity where you can work safely with different problems, and you have this goal to get to. So first, we need to organize the data. We have different countries. Each country can have different years for the values, so we cannot put everything in a neat table, but we have a good way in Python of associating pairs of values, of key and value. So we can do a dictionary for each country, and for each entry in that dictionary, we have another dictionary that has, for each year, what is the value. Even if there are missing values, it doesn't matter because we don't put them in the dictionary, and we only put the values that we have. So basically, we are creating a dictionary of dictionaries, and we can store this information even if there are many gaps in the values that we have. And this would be the data format that we want. So this is one thing that you usually have to think about when you're dealing with data. You have the files, and you need to think about how to put that in memory in the computer, in your program, in order to use that data. This is usually a first important step in order to process data. To read the Excel files, we're going to use this Excel read library. Excel files are actually zip files with XML files inside, so the format is a bit complicated. We're not going to try to parse them ourselves, but we have a library that already does that. So we're going to import the Excel read library, and we're also going to import the matplotlib to do the plotting. Usually you only need to import things right before you use them. So you can put the import at any point in your code. But it's best to put all the imports in the beginning, because then it's easy to check what code your code depends on, what other modules are needed to run your code. So we'll do that. We'll start with the documentation, put all the imports there. If we need to import something else, we also add in the beginning of the code. So this is the function that we're going to use to load everything into that dictionary of dictionaries. It's a bit more complicated than those we've seen so far, but it's mostly it appears complicated, but step by step it's rather simple. The first part, we're going to use the Excel read library to open the spreadsheet. We have this open workbook, the name of the file, so an Excel file, and we get this object which has all the sheets inside this file. Since the data is always in the first one, these files only have one sheet anyway, we're going to get the first one, which is sheet by index. We give index 0. Index 0 is the first one, and now we get this object that corresponds to one page of the Excel file. And now we can access the cells by the columns and the rows for the cells. Like in Excel, you have the coordinates of the cells, and you can go there. So first, we're going to go on the first row here and get the values for all the years. because now we have to know that this column has this year, say 1807, 1808, and this is different for different files. So this is what we're doing here. We start with an empty list for the year, and we go from the column of index 1, which is the second column, because the first column is merely the title of the data that we have here. And we're going to iterate from that one to the number of columns in the sheet. This is the n call here. Note that this kind of information you have to look up on the documentation of the library to figure out how to access. This is not basic Python, it's just where the values are stored, the different variables in the objects and so on. So we are looping through the second column all the way to the end, and we are appending here into the years, converting to integer the value that is on the first row and each of these columns. So this cell value function of the sheet allows it to get the value of the cell by indicating the row and the column of the cell. So we are increasing the call variable from here to here. We are always looking at the first row, and we are getting these values into the list. So now we have whatever years there are in this Excel spreadsheet, we have them in this list of years. And now we're going to start our dictionary for the countries, and we're going to go from the second row until the end. We're going to get the country from the first column in that row. This is the name of the country. And now we're going to create a dictionary with all the values for this indicator for this country. So we're going to start again with column 1 until the end, but we're going to get values from this row and this column. So now we are increasing the rows to get from one country to the other, but then we're going to look for the values in the row corresponding to the country. And here we check if the value on that cell is not empty. So this is different from the exclamation point and equal and an empty string. If it's not empty, then we have a value there. We're going to put it in the dictionary for this country. So the indicators for this country will get the key corresponds to the year. So it's the column where we're at -1 because the year starts on the second column. The first element of the year corresponds, of the year's list corresponds to the second column, and so on. So we subtract 1 there, and this gives us the year as a key. And the value we put there in the dictionary, copying the value into the dictionary. Now we can do something here. This is the name of the file we're reading, but we can discard all countries that don't have enough data. So let's add a parameter here for our function, which is the minimum number of values a country must have before we add it into the dictionary. If it does not have that minimum, then we just discard the country. So we check that here. If we started this dictionary empty, we fill the dictionary by going through the row for this country, and now we check if the number of entries in the dictionary for this country is at least as long as min data, as the minimum number of data that we need for the country. If it is, then we create in this dictionary an entry with the key corresponding to the name of the country, and the value is this other dictionary. And now we keep looping this. So we're adding to the dictionary the entries for those countries that have at least those values in the spreadsheet. So this is an example. We're going to import load table from our module. This module, I called it life qual or life quality, and then life expectancy is the result of loading the table with this Excel spreadsheet, which has the life expectancy. And I put the 40 there. This means that all countries with less than 40 values, 40 years of data, will not get into the dictionary. And now we can find, for example, the life expectancy for Portugal in 2001. This is the key for the first dictionary, which is by country. And then when we do life expectancy for Portugal, we get a dictionary which has the data by year. So we can access that one immediately with the year. So we can change this. We are receiving one dictionary and accessing it again by key. This would be for 2003 and so on. We can test and then check the data. Okay, so now we have a way of loading all the data into these dictionaries. We need to think about how to create the image. So we're going to plot the data by drawing a circle for each country with a specific color, a different color for each country. The X and Y coordinates will be taken from some indicators, for example, GDP and life expectancy, but we don't want to fix our code into that. We want to allow the user to choose what are the values for the X. And the radius of the circle, we'll use some other indicator, but we also want to leave that free. So we want to make the function more general than just for this particular case. To create, we need this, to create a plot, we'll need to create a bit more sophisticated, use a bit more sophisticated plotting. We're going to create a figure, then the axis, which is the object where the actual plot will be done, and then set up everything, draw the countries, and show. So let's see how we can draw the circle for a group of countries. We need to think about first what goes into the function. So the first argument there is the object from the plot, where we actually do the plotting, where we put the markers. Because this allows us to create the image first and then just send the object here to plot with whatever setup we want. For example, if we want to use logarithmic scale or something like that. Then we need the values for the x-axis and the y-axis, and also the value for the size of the circle. So these would be those dictionaries which has, for the countries, the data that we need. And now we need to rescale the size, because if we want to represent those circles, depending on what kind of values we're using, the units themselves, the absolute values, have to be rescaled. Otherwise, we can have circles that are greater than the plot or very tiny circles. So we need to be able to rescale that. This would be the size scale for the circles. And now we need to specify which year we want to plot. And we also need to specify which countries we want to plot and the colors we want to give to the country. So you see, if you want to make a more general function, we start to have lots of parameters. Yeah. This is the axis. So this is the plot object where we can use the plot function. This will be, we will set up the figure and then send that plotting object here for this function to draw. But this is just the equivalent of the plot examples that we saw earlier. I'm going to detail this a bit more, but it's the object from matplotlib that does the actual drawing. And this is where we call the plot to do this. The reason for this is that we may want to set up this first by deciding where it is in the figure, if there is a log scale on one of the axes, what is the range of the axis, and so on. Okay? And this function only draws there. So this way you can do this separately and not inside the function. Okay? So now we have to specify which countries and what color each country will be drawn in. And we can do that in this way. Let's create a list of tuples. Each tuple has two values. The first one is the name of the country, and the second one is a color defined by the red, green, and blue components. You can define any color that you want by mixing red, green, and blue. For example, Portugal is green, so it has 0 red, 1 of green, and 0 blue. If you want yellow for Spain, this is full red, full green, and no blue, and so on. So if you change, and these are fractional, you can adjust the hues and the intensity of the colors in whatever way you want. So this is how we are going to specify the countries. The name of the country and the color we want to draw, and this we receive here, this list. So now we're going to draw them. For each country, we're going to get the X, the Y, and the size values for the plot by looking up the dictionary. And we need to look up the country name and the year in each dictionary. The country name will be the first part here of this information for the country. So basically, we use the country name and the year. We get the X, the Y, and the size. For the size, we compute the square root and multiply by the scale. The idea of the square root here is so that the area of the circle is proportional to the value. And since this size is the radius of the circle, we compute the square root and make the area proportional to the value. So something that has an index twice as large will have an area that is twice as large, but that's not a radius twice as large. Okay? But these are things that you can adjust whatever way you want, depending on how you want the graph to be. And now we're going to plot. We're going to plot at this position, x, y. We're going to use a marker that is a circle, filled with some color. The size of the marker is this one we got here. Alpha is the opacity. If alpha is 1, it's opaque. Alpha 0 is transparent. So you give it an alpha 0.5 so you can see if they are superimposed. We can see them slightly transparent. And this is the color that we want to put. So color is the second element of this tuple, is this three-valued tuple here where we mix the colors. So this is just to give you an example that even though many simple examples for plotting just show a line, you can actually control a lot of things in the plot. Again, you don't need to know everything by heart, but when you want to do a specific plot just like that, you go look at the documentation and you have the list of all the options you can change to make the plot appear the way you want. So the basic idea here is that you remember that you can do this. You don't need to remember how to, because then just you can look it on Google or see examples. So this is how we draw one set of countries in 1 year. Now we set everything up. We import the load table and the circle countries function. So this is in one module. This is in another script that we are writing. And now we load the 3 different Excel files into those dictionaries using the load table function. We set up the color of the countries. We create a figure of this size. And now we're going to create those axes where the plot is going to be drawn. And the reason why we don't do this here is because we don't know how the user, in this function, how the user wants the plot to be made. If there are logarithmic scales, if there is a fixed size for the axis, something like that. So this can be done outside the function. We can create a figure. We add the axis where everything will be drawn. This is the size of the plotting area inside the figure. So we go from 5% to 90% of the figure. And we disable auto scale because now we want to plot the same countries over and over, and we don't want the scale of the graph to change as we're plotting. We set the limits, we set the x scale to logarithmic scale, and we put the labels for the x and y and so on. So again, this is just to show that you have a lot of control over the plotting part, and we can decouple this from the actual function that's doing the plotting. We set everything up, and then we call the plotting function. And again, all of these details you have on the documentation, so this is just a matter of thinking about what you want to do, and then just look up the parameters that you need to fill in. So now we're going to call the function to the plot for these countries for 1960, and now we get an error. We run the code, and we get this error, key error 1960, and you see this is the kind of thing that you will see quite often. And a good thing about errors is that they are not just an error. The interpreter tells us what is going wrong and in which place. For example, it happened here when you call this function, circle countries, and inside this function, it happened here. When we went to find for one country, we went to find the value for 1 year, and the key error is 1960. This means that this dictionary does not have 1960 as a key. We wanted the value for 1960, but it does not exist. And we can see that what happens here is actually that there is no GDP value for 1960 for Germany. So when we want to plot, we get this error. One way of solving this problem is we need to think about what our program should do when there is this kind of error, and then we can implement it in this way. This try except instruction statement tells the interpreter to try to do this, and then if there is an exception, an error, and the error meets this type, then we can tell it to do something else. So in this case, what we want to do is to try to draw the country, But if there is a key error, so if the value is missing, we don't do anything. We just don't draw that country. If you don't have the value, go to the other country and ignore this one. So this way, our program will no longer stop there. So our program will no longer stop there, and we'll just skip the country to the next one. And now we can test this by plotting everything in the same graph. So we receive the same parameters for this function, but we also, instead of a single year, we get a list of years, and now simply draw the countries there for all the years. So since we already have this try except block, if some countries don't have data for a specific year, then they are just not drawn in that year, and the program keeps that. Yes, you could, if you look through the dictionary and check if the key is present for each country. Because you can see that if the year in the dictionary for the country, then it exists. If not, then it does not. So you could check this. But this is usually a more practical way. If you know why the error occurs, and you think, okay, if this error occurs, then it's not a problem, we just skip it, then you can do this try except, and your program will simply move on to the next one. So now we create a figure, we set the upper title in this with this string, we create the axis again, set the logarithm scale, create years from 1960 to 2011 using the range function, and now we give this iterator here so that when it looks through all the years, it will plot all these years from 1960 to 2011, because it will stop one before the last figure is there. And now we get this plot. So we are plotting everything in the same chart, the scale is always the same, and we get everything like this. Of course, if we want a GIF, what we need to do, there are some animation models in matplotlib, but then they only work when the program is running, and this is not very useful. So what you can do is just create a set of images in order, and then it's easy. You can use a program like FFmpeg to create a movie, or you can load it in GIMP and save it as an animated GIF. That part is trivial because you don't need to do anything other than just saving at that format. So this would be the animation we can create. We load the data, we set up the plot for each year, so we create a new figure for each year, we set the title with the year, all that set up for the axis size, the logarithmic scale, and so on. We draw, and then we save the image. And this is what we can do to save. From the plotting library, we have this function which is savefig, that saves the current plot to a file. You give just a file name, and it saves the plot to that file. Depending on the extension you put there, that will be the format. You can use JPEG, PNG, or GIF, whatever you want. There are many different formats, so this basically, PDF I think so too. I don't know if you need to have some library, but I think it works also. And then we close this figure. This is important because plots in memory take up quite a bit of space, and if you're looping and creating lots of them, it's important if you create one, then you close before you do the other, so you don't occupy too much memory. But then we are creating a new figure for each one, and they always have the same axis limit, always the same logarithmic scale, so they are all the same. The only thing that changes are the countries, the positions of the countries. And we can also add this print so we can see the progress, because this takes about half a second for each image. If you want to do 100, you can see the print appearing there. And then you see this when you run, the print will show you what figures it's creating. The name of the figure is simply the year plus PNG, so each one will have a different name, and you can then just group them all together and save the GIF, which is what I did here to create this GIF. So this shows you how you can use this automation to do something that if you were to do by hand, you probably would not do, because to do 40 or 50 plots of this just to get an animation, we would forget and don't do it. But if you have the data, if you need to use the data and just need to write some code to plot it, then it's easy to export like this. And also, all the complicated parts here, if you see, are just the details of how to use the plot and how to set up the plot and so on, which is basically something that you look at the documentation and select the options. The basic parts that are the loops, the conditions, the things that we saw this morning, they are always the same and they're always basic elements here. So even though this may still look confusing, as you keep using these basic elements, things will start to fall in place more naturally. So to sum up, we saw how we can import codes from other modules. And this is important not only when you organize your code, your programs, but also because there are many libraries and lots of code already done to solve most things. So you don't need to worry about all these details of the information. The important thing here is that you start to be familiarized with this process of looking at the code, looking at the documentation, fitting things together. As long as you understand the basics, how to fit things together, how to write a function, how to do conditions and loops and so on, the rest is just looking at the options in the library and setting up the parameters for whatever you're using. So if you're reading files with some format, you need to know how to specify the delimiter and how to skip headers or things like that, but that's in the documentation of the function you're using. If you're plotting, you need to know how to set the colors and the scale, but that's also in the documentation. So those things are not really programming, you just look at the documents and apply the parameters. The thing that is most important here is that you know what is possible to do with this, and you have an idea of how to fit the pieces together to get your programs working. So the more you work with this, the easier the details will come. So if you do plots for a few months, then you already know by heart exactly how to set up the plot and so on, and that saves time. But that's really not necessary to do plots. You can just go on Google and see what the parameters for the plot function. What's really necessary is the getting used to thinking about the problems in this way, of composing the different parts, of disassembling the problem and then assembling the solutions to solve them. So now, for this week, I suggest, after this lecture, we have until about 6 o'clock, or as long as you can last, because this sometimes is a bit tiring, but I would advise you to try to look at all the things that may be obstacles for when you're looking at this for yourself, and clarify them with me. I can help with those questions. And then during the week, with more time, you can try different exercises. You have the code for these examples in the lectures, code for some of the tutorials, except for the ones for the evaluation. So you can always look at the solutions, but also you should try to think for yourself how you would solve that problem and to start trying to implement these things. Okay. If you want to see more about the console that you have there, because that IPython console is useful also for interactive analysis. You can see the plots, you can see the graphics immediately, you can easily see documentation or see the variables that you have in memory and things like that. So if you want to invest a bit more in that, especially if you do a lot of interactive analysis, instead of only writing code, you can also look at that. But we're not going to focus much on the console, we're going to focus only on the part of the code.